All right, it says a test plane flies in a straight line. That's what we do. In 2004, this was on the test in 2004, and its velocity is given in this table at different times. Again, I'm just going to let myself know, okay, those are velocity values. Based on the table, what is the smallest number of instances where the acceleration could be equal to 0? If I gave you velocity info, what do we have to do to that to get acceleration? Take the derivative, but if I only gave you points, we would just take the change in y over change in x, or change the slope, or let's find the slope, right? That it could equal to 0. Between 0 and 40. So if I were to find my slope right here, if I did change in y over change in x, I don't even care about what the value would be. Would it be positive or negative? Be positive. 9 minus 7 would be positive. 5 minus 0 would be positive. So I'm going to say the slope here would be positive. What about my slope here?
Positive.
Yeah, I agree. And my slope here? Because again, if I was just doing change of y, 7 minus 9 would be negative over 15 minus 10. Okay. Here? Still going to be negative? I agree. Keep going. Negative again?
It's 0.
Ooh, slope is 0. Positive. Positive. Okay, so it says, what is the smallest number of instances? Smallest number of instances where that acceleration could equal 0. Thoughts?
We know there's at least one.
We know there's one because it says 0.
Yeah.
Any others?
Wherever it changes from positive to negative.
Or negative to positive? Well said, Mark. Is there another time? Yeah, between 10 and 15, didn't it change signs? To go from any positive number, 10, to a negative number, negative 3, wouldn't I have had to pass through 0? So even though we're staring at a 0 here, we're going to say twice. We're going to say at least twice. We're going to say based on the values, what is the smallest number of instances? We'll say 2. 2, because my velocity, and instead, we often want to say it, but we're going to just say v of t, change the signs, or equals 0 from, and we'll probably say our time frame again. Here we go. Okay, 2022 test now. Particles are moving along the x-axis. Woo! Crazy times here. It's position. Wait, haven't we already done this problem? We already did this problem. So when it says rates of change, this is really, again, just putting these derivatives into real world. Rate of change will help us predict how quantity will change over time, like your speed, right? What I'm doing as I'm driving. When is quantity increasing, decreasing? How fast is that quantity changing? Derivative notation is not always used, and we've seen this already. A of t could represent a rate that, say, water fills a container, which is technically a derivative, which would technically be a prime, but they can name it whatever they want. Rate of change could be given as a graph, table, or an equation. Okay, so this is how we could start looking at this now. It says people enter an amusement park at this given rate. So again, I'm going to let myself know this is a rate. That's really an E prime, if you will, even though they just named it E. E is people per hour. Okay, T is hours after midnight. Interesting. Use your calculator to find E prime of 11. Using correct units, interpret the meaning of this value. So let's go get our CALC, and they want E prime of 11. So if they want E prime, we're going to do a little math 8. We're going to math 8 that equation. 15,600 over x squared minus 24x plus 160. And what do you think I'll do for my x? X equals what? 11. Because that's that right there. Boop, boop. And your work for this problem for AP would just say E prime of 11 would equal 107 point blank, blank, blank. Or maybe I'll start this one off. I'm going to say, and again, the order that you write it doesn't have to match my order, but we just have to get all the same info. At what time would it be? Yeah, if this started at midnight, 11 hours after that would be at 11 a.m. At 11 a.m., and again, since we found an E prime, I'm going to say rate. And then I'm going to just use the words that they said. People enter the amusement park. People enter an amusement park. It's going to be like the seniors on their senior trip this year. We need the word increasing or decreasing. Our answer was positive or negative? Positive, so we're going to use the word increasing. Oh, and then, yes, even though we already said rate, wasn't E a rate in itself? E was already a rate. When we took the derivative again, we got to do another rate. Increasing at a rate of 107.958. Use those units. If it was people per hour, what's that unit going to be now? Look at my font. What happened? What? Oh, that was so weird. People per hour or people per hour squared. What is happening? We're going to say, oh my gosh, people per hour squared. So that was good. Now, I wanted to just kind of put this into units. If my Q of T, Q is just a quantity. If the derivative of that is equal to 0, then that quantity is not changing. But if my quantity is increasing, what do you think the derivative would be? Greater than 0. And if my quantity is decreasing, my derivative would be less than 0. Good, good, good. Okay. And then it says a local bakery opens at 7 a.m. The number of people in the bakery, that is not a rate if you ask me. That's just the number of people, is B of T. When T is at 7 a.m., T is 0. Is the number of people in the bakery increasing or decreasing at 1? Number of people increasing or decreasing. If we're curious if a quantity is increasing or decreasing, I got to go find the derivative and see if it's positive or negative. Cool? So if this is B of T, let's go find B prime of what X value do you think?
I think 6.
Yeah, how'd you get 6?
Yeah. As 12 a.m. is 5 hour. Wait, no, 12 p.m. is 5 hours.
Well, real fast, hold on. This equation starts at
7.
At 7. And 1 p.m. is how many hours after 7 a.m.?
6.
Yeah.
As 12.
You guys, did I say calculator active? I didn't, but I meant to. Let's go get our calculator. Did anybody get negative something? Negative 28 point? 3 decimals. Let's talk units real fast. It didn't ask it. Let's just put it though. If this was people in the bakery over time, and the time is hours, what would this rate be? The amount of people in the bakery is, yeah, people per hour. People per hour. But would we say the number of people, again, I'm looking using the words that they write right there. The number of people in the bakery is increasing or decreasing?
Decrease.
Yeah, because that was a negative. At a rate of positive or negative do I write now?
Positive.
Since we said decreasing, then we just use the positive. Agreed. So then we're going to say 28.172 lobbly people per hour. Okay, let's take a peek at this. Some quantities are determined by 2 rates, a rate in and a rate out. And this one's very kind of morbid, what I'm about to tell you. But penguins are going to be born at a certain rate, and then they're going to die at a certain rate. Okay, that's kind of morbid. But we want to compare it. It says to find out whether a quantity is increasing or decreasing at a specific time or interval, we could always compare that rate in versus that rate out. So it says a penguin population on an island is modeled by this differentiable function P of T, which they didn't give it. There are 100,000 penguins on the island to begin with. Then the birth rate, I'm going to say the birth rate is B of T, that's a rate. And then the death rate, D of T, is given there. Is the penguin population increasing or decreasing at t equals 5? Yeah. Yeah. Okay, so what would we do? We've got to go find what b of t is, or b of what instead, actually? b of 5, right? Could we go find what b of 5 is? Would we need b prime? It says b of t is a birth rate. I don't need the derivative of that because then that'd be the acceleration, right? Let's go find what b of 5 is with our CALC. B of 5. Anybody? I got 1349.859. Get D of 5. The death rate at that moment. Perfect. Now, you were exactly right, Ritz. We could do this one of two ways. Right off the bat, you said that you were going to subtract them. And you can. What would that tell you when you subtracted them?
Births minus deaths is the growth rate.
Yeah. And if it was positive?
It would be increasing.
And if the births minus deaths was negative?
The deaths would be higher.
Perfect. Very good. So we could do it one of two ways. You could totally write it that way, or you could just say if the birth rate at 5 was bigger than the death rate at 5. So we could even just say since B of 5 was bigger than D of 5, we're going to say the penguin population was, is increasing at T is 5. The rate people enter a museum. Okay, rate of people are coming in the museum. It all got started because of this word museum. Okay, in people per hour is given by M of T. M of T is a rate. Notice that, okay? Graph of M of T is shown, and then starting at T equals 1, people start leaving the museum. Oh, and when they leave the museum, they just gave you that rate. Find M prime of 3. Find M prime of 3. M is the rate people enter a museum. And then it said the graph of M is shown. This is M of T. How are we going to find M prime of 3? Biscuit, this kind of goes back to your question from your test. Guys, how do we find M prime from this graph? Get the slope when X is 3. Could I take the slope of any part of this line? You probably can't see those numbers very well on this terrible. Sorry. Could you use this though? Up.
It's 20. 20 per square.
Yeah, it goes 20. It goes up by 20s, you guys. I'm the worst. Sorry, 20, 40, 60, 80, 100. Sorry, Bob. I know, Bob, I'm sorry. So what's going to be my slope? Rise, 20, run, 1. 20 over 1, 20 over 1. Okay, so we're going to say M prime of 3 equals 20. Oh, and what would be those units? And this says use the appropriate
People
units.
per hour.
Yeah, because M was people per hour. M was a rate. M was people per hour. So we're going to say the rate people enter a museum is increasing or decreasing? Isn't it increasing?
It is kind of confusing because it says at 1, people started to leave.
Oh.
The graph doesn't show that.
Oh, I see what you're saying. So I guess I was thinking M prime of 3, you're right. I was thinking that they just wanted to know the rate of people coming in. But no, you're saying if the rate of people coming in was, I'm going to just finish my sentence, but then you're right. We should include.
Well, that's what
Ow.
B is.
That would be,
Say it again.
That's what B is talking about.
B. Oh, what is the rate of change of the people in the museum?
This one's just the rate of people entering, not the rate of growth.
Good call. Because they are saying, yeah. What is the rate of change of people at the museum? Good call. This one's talking about at. This one's asking since M is the rate people enter. When they just ask for M prime of 3, that's just going to be the rate that they are entering. Good call. The rate of people entering a museum is increasing at a rate of 20 people per hour squared at t equals 3. Okay, then it says, what is the rate of change of people at the museum? So, of course, yes, people are entering the museum at 20 people per hour squared, but then they are also leaving the museum at 45 people per hour. Okay, so what do we think? We've got to go find, my bad. We don't, when it says, what is the rate of people, what is the rate of change of people at the museum? My bad. I don't want to use this 20 here because this is m prime of 3. What is the rate of people, rate of change of people at the museum? The rate is just m of t, right? That is my rate. So I'm going to just say, well, what is m of 4? And then if people are leaving at a rate of 45 people per hour, I'm going to subtract that 45. From this graph m of 4, Bob, can you read the actual value? What would m of 4 be? It's like I can't read it because your graph is so terrible. Yeah, I think it's going to be 80. I know it's going to be 80. So we're going to say 80 minus 45. So at 4, what is the rate of change of people at the museum? 35. What would be my units? Nice. People per hour. So to start 4-4, introduction to related rates. Okay, we've seen when we're given a function y, we found the derivative is always dy dx. Always, always, always. And that is going to be, that's just saying find the rate of change of y with respect to x. So that's what we've always done. Whoops. That's what we've always done. So I said, hey, go find dy dx of this function. Let's go find the derivative of this function. So the derivative of y we could say is y prime or just dy dx. You know what the derivative of 3x squared is. 6x plus 6. Okay. But then look what I say. I say now, suppose x and y are both functions of time. So again, now we're finding these derivatives with which more respect to the real world as opposed to just x. So now we're talking about with respect to time, t. So instead of finding dy dx, because before it was always with respect to x, now we're going to go find dy dt. Okay? Or what if I'm taking the derivative of an x? That would be a dx dt. Very good. So everything is going to be the derivative with respect to time. Now, why didn't I ever have to worry about the derivative of the x before?
Because dx over dx is 1.
Right. So the derivative of y we know is dy dx. The derivative of 3x squared would technically be 6x dx dx. And anything over itself we never had to worry about because it was always with respect to x. It was all cool. We never had to worry about it. But if they change our with respect to time, now everything has to have a derivative with respect to time. So as we go attack this one over here, the derivative of y would be dy dt now. This is funky because we're talking about rates over time. The derivative of 3x squared, still 6x dx dt. And the derivative of 6x is still 6 dx dt. Okay? So that's a nuisance. Okay? And they're going to let us know when we're finding derivatives that with respect to time. So check this out. It says find an equation that describes the relationship, blah, blah, blah. Oh, okay. So sorry, we just did that right here. Okay, we just did that. Okay, I say this because I want us to just practice setting up an equation and taking its derivative with the respect to time. So it says a rectangle is undergoing changes to its length and width. We could have a rectangle that might be growing lengthwise, might be growing widthwise, or it might be growing bothwise. And it says find an equation that relates how the perimeter of the rectangle is changing over time. You guys, if I've got a rectangle with length and width, what's the perimeter of that?
2L plus
2L plus
2
dubs, right? So then it says, hey, find the equation how the perimeter in the rectangle is changing over time. If they want how it's changing over time, guys, we got to go take a derivative. The derivative, the rate that the perimeter is changing, how I'm going to write that is I'm going to say dp dt. And what that means is the perimeter is changing at this rate over time. The rate the perimeter is changing over time. What do you think the derivative of 2L would be? Just treat it like 2x. Derivative of 2x? 2. Derivative of 2L? 2 d L d t. Whew, Miss Meister. Okay, you guys, how about this? Says suppose x and y are both functions of time, and I've given us this equation. Find the equation that describes the relationship between the rate of change of x and y with respect to time. All they're asking you guys is take that derivative. Derivative of x squared, we know, is 2x. With respect to time.
Yeah.
So we'd have 2x dx dt, you got it. And
3 dy.
3 dy dt, thank you, Coop, equals nothing. Very good. We're back to our rectangle, but now it says it's changing its length and width over time. Again, wouldn't that change its area as well? What's the area of a rectangle? Yeah. Area is just length times width. Big L's are big. Well, I typically would have done littles, but I want you to feel good about your, when we take this derivative. Ooh, who's going to throw something at me on this one? Product rule, says Dean. Look how excited Miss Meister is. I know, derivative of area with respect to time. Very good. Derivative of area with respect to time. That's how we write it. You got it. And then we got to do product rule. Oh my gosh. We got a fig and a gif. F prime, the derivative of L. dL dt.
Evil.
I know, times G. Plus G prime. dW dt. Times F. Perfect. A circle is undergoing changes to its radius. Find the equation that relates how the area of the circle. Area equals pi r squared. Pi r squared. Derivative of area with respect to time would be dA dt. Derivative of pi r squared. 2, we just bring that exponent up front. 2 pi r dr dt. And you're like, what did he just do? He's just saying, I got to bring my exponent up front because this is just really a constant.
Yeah.
2 pi r, bring my exponent down by 1. This is chain rule. We took the derivative of the outer, we left the inner, times the derivative of the inner. My only variable is r. The derivative of my radius with respect to time is dr dt. Whoa.